Hello everybody. I made a video for you guys today just to kind of review what you've been going over. You had a worksheet yesterday that dealt with rotational work, and you will be finishing that today if you did not get it done. So for your bell ringer, you want to write all these down in your notes, and we're going to write out what each of these are, what each of the variables are for each equation. Okay, so pause the video please, take a few minutes to write these down, and then start it back up again, and we'll start with the notes. Okay, so there's an equation that I have on the worksheet for you guys. It'll be coming later in the slides here, but we have our general work equation over here. Okay, so work equals force times distance. My smartboard wants to work for me, so that's work, and it's measured in joules. That's my force, and that's measured in newtons, and I'll have to write the English too, so it would be foot-pounds, and then it's also pounds for the force, and then the distance is going to be, that'll be in meters, or that should be in feet. Okay, so then the next column over here we have work theta, so that's rotational work. That's what we're going to talk about a little bit more today. Okay, so theta is the radian or degree measurement that you are applying our force through, and normally our force is caused by a torque. Okay, so this is really the equation that we're using. Work equals torque times theta, T theta, where theta is in radians. Okay, and then we have our mechanical advantage equation over here. So that's just force out over force in. It's also distance in over distance out. Okay, and then we have our efficiency here. So we got work output divided by work input times 100. Okay, so these are all the equations that we're using except for one more that I'll give you here in a little bit. But let's check out some of the questions from the worksheet. Okay, so if you wanted to double check these, you'll need a calculator, just because the radians, we're working with like pi and stuff like that. So I had the conversion at the bottom of your worksheet. Excuse me, and that's 1 radian equals 57.3 degrees. And then we also had 1 revolution. That's going to be 2 pi radians, and that's also going to be 360 degrees. Okay, so we're going to convert everything here. And we're just going to use, it's going to be a pretty simple setup here. We're just going from left to right, and we're going to find a torque. Okay, we're going to find a torque with our information that we're given, and then we're going to take that times theta, and that's going to give us our resulting work. Okay, so torque is just force times lever arm, and we have a force of 3 pounds and a lever arm of 2 feet. Okay, so we just multiply those two, and we can get a torque of 6 foot-pounds. And then we have 180 degrees. Let's convert that to radians. So if you wanted me to do some tracks here, I'll write it off to the side, then I'll erase it. 180 degrees. Well, we know that there's 57.3 degrees in 1 radian. So let's do that little quick conversion here. All right, I think tracks are probably the way to go with these. 180 divided by 57.3, and we get 3.14. So that's pi, actually. So 3.14 radians. So let's get rid of this. And now we can just multiply from left to right. So it's torque times theta. So that's 3.14, which is just pi times 6. And we get 18.85. I like to go to the second place. So that's 18.85 foot-pounds or pound-foot. I think I think work is written in pound-foot, but foot-pounds is better. Let's just write foot-pounds. Okay, so they're all pretty much the same there, except we see ones like this and that, and then we also see we might have to do a little bit of conversion on some of these. Okay, so it's just kind of a lot of conversion practice and just throwing stuff in our formula. So this one right here, what we're looking to do is convert that to a force. So this is your mass. Okay, so if we have a 5 kilogram mass, how do we turn that into a force? We're going to take it times 9.8. So 5 times 9.8 gives us a force of 49 newtons. So then we can just do force times lever arm, so 49 times 4. You get 196 newton meters of torque. And 1 revolution, so that's up here, 1 revolution is 2 pi radians. Okay, or it's 2 times 3.14, so now I can just multiply from left to right. 196 times 2 pi. And that gives me 1,231.5. And that is in 50 if you want to, that's newton meters. Okay, let's practice a little bit more conversion here. So this stuff here is pretty straightforward. We've done torque before. So I'm just going to work on some conversion here so you guys can see that. So let's convert the next one here. So 30 degrees, just like I did before. 30 degrees, set up tracks, 57.3 degrees, that's 1 radian. So it's just going to be 30 divided by 57.3, and you get 0.52. Okay, and I'm going to back up a little bit here. I know I said I don't want to use terms of pi, so I could just do 2 times pi, so that's 6.28 there. Okay, so then 270, do the same thing, so it'll end up being 270 divided by 57.3, give me 4.71 radians. And then all of these you could just kind of keep dividing by 57.3 to get there. Alright, so down here we have a few of them that are a little bit trickier. We got revolutions into radians. So you're going to use that 2 pi conversion or that 6.28. So let's just treat it like tracks. So 0.25 revolutions. Well, we know that there are, so in 1 revolution, we're looking to cancel out the revolutions so that they go opposite each other. There are 2 pi radians, or 6.28, whichever one you prefer. I want the answer in decimals though. In the conversion, that's okay to use it, but then it'll turn into decimals in the end. So we're going to take 0.25 times 2 pi or times 6.28, and you get 1.57. Okay? Now all of the rest of these, right here, work just like that. You're going to take each one of those times 2 pi because we're using revolutions here. So 250 times 2 pi, that's going to be a bigger number. So 1,570.796, so it'd be 0.80. So 1,570.80. So that's a little bit larger number. Okay, and that's pretty much how you do your conversions. So tracks helps. So I would suggest using tracks when you're doing these rather than just trying to think about it. Tracks are probably the quickest way to do it. Another question on the worksheet I wanted to look at quick, and I'm going to kind of jump ahead of the lesson today, was the one where a child is pulling a sled and we have an angle, a rope at an angle of 30 degrees. And I think I wrote on your worksheet, use work equals FD cosine theta, and I'll explain why here in a second. But it's we have to do work, and work is force in the direction of the motion. All right, so we have a force of 45 newtons. We have an angle of 30 degrees. And then A, so that's how much work is done if the child moved the sled 15 meters. Oops. So our distance equals 15 meters. So we have a kid pulling a sled. We got our rope. Maybe we got another kid on there. Okay. but that is at an angle of 30 degrees. And I'm showing you now so I can save time later. But he's pulling at an angle of 30 degrees. And remember, in order for work to be done, it has to be in the same direction of the motion. So the sled is moving that way. Okay, the sled moves that way 15 meters. However, I'm pulling on the rope that way. So if we think about vectors, those vectors aren't going the same direction. So we'd have to find what vectors are going the same direction. All right, well, you guys remember from geometry, if I have an arrow or a vector like that, then I can actually make a right triangle out of it. So that's 30 degrees. And this right here is the force of 45 newtons pulling on the rope. So then you have to use your sine, cosine, tangent stuff. So if I want this one right here, I'm going to use cosine. So cosine 30, so cosine is SOHCAHTOA. So C-A-H, oops, let's use the capital A there. So that's adjacent over hypotenuse. So that sets up a ratio of x over 45. And then to get the x, we would multiply both sides by 45. And you get 45 cosine 30 degrees. Okay, so that's where you get the cosine theta part of it, because we want the horizontal component, or the force that's in the same direction of the motion. So we're going to have 45 newtons times 15 meters times cosine of 30 degrees. And when you're doing this in your calculator, you want to make sure that your calculator is in degree mode. So if you press on the blue ones, you press the second button, and then, well, it looks like we might be good on the blue ones. Okay, so on the yellow ones, there's a mode button. You have to press mode, and then it can switch for you. Oh, so on the blue ones, you don't have to push second. You just push the button that says DRG right next to the second button, and then you can pick degree, radians, or gradians. So you're just going to go with degrees. So then it'd be 45 times 15 times cosine 30, and you get 584.57, and that is Newton meters. So that's how much work the child is doing pulling on the sled. So then the question is, how much work would have been done if the sled had been pulled just horizontally, so straight horizontally? Okay, so you got your kid like this, and then, I don't know, maybe there's a hill or something that the sled's on. Okay, and he's pulling it straight horizontal. So that's not the best model, but just straight like that. Or maybe he's sitting on the ground pulling it. Okay, so there will be no cosine there. So work is just force times distance. So our force is 45 newtons. And the distance, again, is 15 meters. So you just multiply those two out, and you get 675. And that's Newton meters or joules. Okay, so you can see here that you have to actually do less work when you're pulling something at an angle, which is kind of nice. So that's why we have things that work on angles. Okay, so your job is to finish that worksheet later on if you didn't get that far on it. Okay, but for now, I want you to put the worksheet away, and we're going to do a few practice problems. This will be some problems like what you'll see on the test. Okay, so put everything away except for a sheet of paper or maybe your notes, and we'll practice some problems here. All right, so I'm going to kind of skip around a little bit here. We've already kind of done this, and you're going to get more practice on your worksheet. So I want to skip ahead to problems that are more like word problems like this one. So a lug nut is loose on your truck, so you need to tighten it. You use a wrench that's 1.5 feet long. You apply a force of 10 newtons to the wrench and rotate the lug nut 3.5 times until it's snug. What is the work done? So you are not given a specific degree measurement here. All right? but we're going to write out everything that we have and what we need to do. So we have our lug nut here, okay, and we have a wrench, whatever. So the wrench is 1.5 feet long, and we're applying a force of 10 newtons down on the wrench, and we're going around 3.5 times until it's snug. Okay, so we know, since we're rotating something here, work is going to be torque times theta. Okay, so I'm going to write off to the side what torque is. So torque is force times lever arm, or radius. Okay, the radius, or the circle that you're rotating around. And then we can go from there. So we have, let me write some stuff over here. We have a force of 10 newtons. We have a radius of 1.5 feet. Okay, so then we have enough information to find torque. So 10 newtons times 1.5 feet. So 10 times 1.5 is 15. So now we have a torque of 15 Newton meters. And actually, I just realized that we did something, or I did something wrong here. Because if we're using newtons, we have to convert to meters. So that means we have to change the feet to meters. It's not 15. Okay, so catch your errors, just like I tried to do there. So 1.5, there's 3.28 feet in a meter. So 1.5 feet, 3.28 feet, 1 meter. So 1.5 divided by 3.28 is going to change our problem quite a bit. So 0.46 meters. Sorry about that, people that were questioning it. Okay, so that'll give me 4.6 Newton meters. Okay, now we got to figure out what that theta is. Okay, so it said we're going to rotate the lug nut 3.5 times. So that means we're going 1, 2, 3.5. That's 3.5 revolutions. So we convert revolutions into radians. So 1 revolution is 2 pi radians. Well, that's 6.28. Put that in your calculator, and you will get, so 3.5 times 2 pi is 21.99. And that's radians. Now we got what we need to plug into our formula. So work is going to be 4.6 Newton meters times 21.99 radians. So put that in your calculator, and I get 101.16. And that is Newton meters. So you're doing 101.16 Newton meters of work on that lug nut. Okay? So that's how they work. These are going to be a little more involved. You're going to have to try to pick out what you need and pay attention to your units, like I did not when I started here, because you might have to do a little bit of conversion here. Okay, so let's try this one. So pause the video for a little bit, give it a shot. It's pretty similar to the last one, and then we'll come back and I'll work through it. Alright, you're pedaling a bike down the street. Pedals are 12 inches long, and when you pedal 4 times with a constant force of 5 Newton, the bicycle drives 20 feet. What's the work done when you pedal the bicycle? Okay. Well, we have quite a bit going on here. Okay. So we have 12 inches long, pedaling 4 times, a force of 5 newtons, and our bicycle's going 20 feet. What's the work done when you pedal the bicycle? Okay. Well, that drives 20 feet is not going to help us out that much, because if we're doing work on the bike, then that's the work done on the pedals, okay? So our work pedaling will result in the 20 feet. So we don't really need that. I know you're saying, well, work equals force times distance. Well, that would be if I were pushing the bike. If I push the bike with 5 newtons, 20 feet, then I could just take 5 times 20. But we are rotating the pedals with our feet, so we're doing work on the pedals. Okay, so we need work equals torque times theta, and we need torque equals force times lever arm or radius. Okay, so our force on the pedals, 5 newtons. Again, here you see that we have inches. So we can't do inches here. We got to convert inches to meters. All right. So however you want to do it, inches to feet, feet to meters, or inches to centimeters, centimeters to meters. Either way is fine. So there's 2.54. I'm going to go centimeters or inches to centimeters. So that 2.54 should go on top. So 1 inch, 2.54 centimeters, and then there are 100 centimeters in a meter. So 12 times 2.54 divided by 100, we get 0.3048. And just for the sake of having a better answer, you probably want to maintain as many decimals as possible here, and then round to 2 decimals at the end. So that 0.0348, that is our lever arm. All right, so we're just going to take those two. So 5 newtons times 0.3048 meters to get a torque of 1.524, and that is Newton meters. Okay, now we can use that in our other equation. So work equals our torque, which we found, 1.524 meters times theta, which we got to figure out. So that's where we got to go to that. You pedal 4 times. So that's 4 revolutions. And again, 1 revolution, 2 pi radians. Multiply that out. 4 times 2 pi, you get 25.13 radians. Okay, so let's throw that over here. Come on, computer. And then we can put it in our calculator. So 25.13 times 1.524, we get 38.302. So that's Newton meters. So that's how much work it takes when you pedal 4 times. Okay. Again, we don't need the 20 feet because the pedaling is not in the same distance as the drive of the bike. Okay, so a little tricky. Okay, let's try one more here, and then I'll have the video uploaded so you guys can look at it if you need to. So this slide is just going to show you that work equals force times cosine times d, and I had it as F d cosine theta. So that's another formula that you want in your notes, okay, just for practice. Okay, yeah, below there. Remember that stuff you learned from geometry, so it comes back, right? So we have that horizontal component there, whatever angle. In order to get that horizontal component, you want to use cosine. Okay? So go ahead and give this one a shot. They're pretty easy once you know the formula. If you didn't know a formula, it might be kind of difficult. Okay, so, and we are missing a piece of information here. We need a distance. Okay, so let's say you pull the duck 5 meters. Okay, now you have enough information to do that one. So pause the video for a minute or two, work through that one, and then I'll give you the answer. All right, so we're pulling that wooden duck. We have, work equals F d cosine theta. So we have a force we're pulling with, 3 newtons. We have a distance that I had to add. So we're pulling the thing 5 meters. And the rope is at an angle, the rope is at an angle of 45 degrees from your pole, from the horizontal. Okay, so I'll just throw that in your calculator. 3 times 5 times cosine 45, and you'll get 10.61. And that is Newton meters, since everything is in newtons and meters. Okay, so that's how those problems work. I think that's about as much as I wanted to cover. Okay, so if you wanted a little bit more practice, I am going to work through these. However, you can stop the video right now and complete your worksheet, and then there could be another video for the sub to play. So thank you. I'll work through these for you. If, like I said, if you want to check them later, it'll be on YouTube for you guys. All right, so wheelbarrow 3.5 feet long. You apply a force of 150 newtons to get it off the ground over an angle of 45 degrees. What's the work done to get the wheelbarrow off the ground? Okay, so there we got our wheelbarrow here. Got the wheels, the handle. Okay, he's got a hold of the handle. So he is, well, that's 3.5 feet. And he's lifting it up off the ground through an angle of 45 degrees. Okay, and the force is 150 newtons. So when you start these, it's best to first find the torque. So work or torque equals force times lever arm. So the force is 150 newtons, and lever arm's 3.5 feet. So we have to convert that. So divide by 3.28 feet to get meters. And you got 1.067. So times 1.067. Let's throw our meters in there. And then we get a torque of 160.06. And that's Newton meters. Okay, so we can use that now. So our work equals torque times theta. So torque is 160.06 Newton meters. I'm going to run into my work. Let's move it over a little bit. Times theta. So theta is 45 degrees. Oops, we don't want 45 degrees. We want radians. Okay. So let's convert. So 45 degrees, 57.3 degrees is 1 radian. So it's just going to be 45 divided by 57.3. And you get 0.79 or 0.785. I think 0.79 work. I know I said use as many decimal places as possible, but I'm keeping that answer in my calculator. So times 160.06, and we get 125.7. And that's Newton meters. Okay. So on top of this one, consider the previous problem. You walk 10 meters forward, applying a constant force of 50 newtons. What is the work done on the wheelbarrow? Okay, so now this one, I'm not lifting it anymore. I'm just kind of holding it at that 45 degree angle, and I'm walking with it. I'm pushing it. Okay. So let's say we got our wheelbarrow here. This is 45 degrees. And we're pushing it that way. Okay, so your brain should have said, well, we're pushing something on an angle, or pulling something on an angle, so that means we're going to have to use our equation with cosine. right? Because we're moving it, we want to figure out the amount of work moving it. So we got a force of 50 newtons. We got a distance of 10 meters, and we have that angle that we're holding it. Let's double check. I think it was 45, yeah. Our angle was 45 degrees. So let's just throw that in our formula. Oops. 10 looks too much like a parenthesis. 10 meters and cosine 45 degrees. Just put that in your calculator. So that's going to be 500 cosine 45, and you get 353.55. And that is Newton meters. Okay, let's double check. Yep, I had meters there. Okay, so that is your work done when you're pushing the wheelbarrow. Okay, so I think that's good enough. One extra problem if you needed some help. So that's all we got for you. Thanks for listening. Have a good one.